Hello.
Yeah, hello. Yeah, can you hear me?
Sir. Sir,
Okay.
we totally have three assignments are completed, sir. But
Okay.
you can't receive any assignment solutions every week after submitting assignments.
Uh, the thing is that we have a fixed time for giving this session. Okay, and this time is not fixed by me. It is these rules are fixed by NPTEL only. So I have to follow that rules only. That is the thing.
Okay, sir, but remaining courses they will release the assignment solutions after submitting, sir. Only
Okay.
optimization in civil engineering course is not received.
So they haven't really released the solutions yet. That's what you were saying.
No, sir. Till now, any assignment solutions are not received.
Okay, for this course, right?
Yes, sir.
Okay, I will drop a mail to the faculty, or you can also to drop a mail to the faculty, right?
Okay, sir.
Just drop a mail to the faculty and CC and PTL. Okay, so
Okay.
I think then they can release the solutions. I think there is some problem. Maybe they have some glitch. Maybe
Okay, okay, sir.
just tell me if there is no reply. I will directly contact the faculty. Okay.
Okay, sir.
Okay. Yeah. Okay then. Yeah. We'll start today's session. So yeah, welcome. This is Diljit here, and we'll be having this lecture 4 of this optimization in civil engineering course. So today we'll be looking through the contents that have been taught in week 4. That is convex function. What is a convex function? How to identify convex function, and like now methods to solve, like what are the like unidirectional method to solve multivariate problems. So, as you have already seen in the class, is a convex function is defined as a function where for any 2 points, suppose if we have x1 and x2, and for a given lambda between the range 0 to 1, the following condition is satisfied. That is, the condition says that the chord joining the 2 points should be above the graph of f of x. So that is the whole condition of a convex function. And if it is less, and if the chord is below the function f of x between the 2 points, then it is a concave function. This is a basic difference between a convex function and a concave function. So in a convex function, like you'll always have a minima, and for a concave function, you'll always have a maximum. So these are the basic definitions. Okay, and then we have some methods which are used to solve this multivariate optimization. One is the univariate search. Second is a steepest descent method. Third is a Newton's method, and fourth is a conjugate direction method. And these all these four methods are based on the direction of search. We'll find an optimum direction. We'll find an initial point, and then we'll see find an optimal direction for on which we'll have to proceed to get reach to the optimal solution. So all these four methods are based on that basic concept. So in this class, we'll be discussing the first three methods only. Conjugate direction method we'll be seeing in the next class or the next week lecture. So what is univariate search? In univariate search, a multivariate problem is converted to a single variable problem using this formula. That is xt plus 1 is xt plus a into dt. So the next point xt plus is the point at step like the second next iteration, and xt is the value of x at the th iteration, and a is a arbitrary constant, and d is the direction, that is on which direction we are proceeding. So how do we identify d? So the d is we should always select d so that we can have a optimal, like the steepest descent direction, so that we can reach to the optimal solution as fast as possible. So to get to that direction, that is the descent direction, we will have to meet a condition. The condition that states that the direction dt is the descent direction if at any point xt, uh, del of f of xt into dt is less than 0. What is del of f of xt? Del of f of xt is the gradient of the function. We are taking gradient because f is a multivariate function. Here x doesn't mean it is only one variable. X means is a variable of x1, x2, x3, x3, x4 like that. So if this condition is satisfied in the vicinity of xt, then we are in proceeding in the descent direction. So if we have identified the descent direction, and yeah, and yeah, I will show how to calculate gradient and all. I will be solving the problems. I will then show how to take the gradient, everything. This is just the concept I am showing. So, so this condition is like that. If you are going for a minima, suppose we want to go for a minima, then what should be the basic condition? The basic is that the second point, suppose this is the first point, then what we want? We want that the second point, that is, this is suppose xt and this is xt plus 1. So we want that the function value at xt plus 1 should be less than equal to x, less than equal to f of xt. So if that is the condition, then this value should be less than equal to 0. And this, so how we came to the condition? This comes from this intuition that we have already seen that f xt plus 1 is equal to xt plus a dt. Here similarly, in the same concept, we are writing the whole equation in this format. That is f of xt plus 1 is equal to f of xt plus alpha into del of f of xt into dt. So to, and we know that f of x, we want that the f of x of t plus 1 should be less than equal to f of xt. If we have to meet that condition, then this whole term should be less than equal to 0. So this is the condition for getting a descent direction dt. Now what is the steepest descent that we can get? So we can see, so the steepest descent is that the minus of del of f of xt. So we can have any direction. Suppose if this is a direction, suppose we have, I am not showing it properly because this is, I cannot show a 2D 3D plane here. I am just showing in 1D. Suppose this is one point, initial point, we want to reach to that point. So our direction, this is the direction should be like this. But we can first proceed like this and also like this, then this, then this. We can take a lot of directions. In all the directions, we will ultimately go to the uh, optimal solution, but we will reach the optimal solution as fast as possible if we take this direction that is directly joining the 2 points, and this direction is directly is equal to minus of the gradient, that is the gradient between the 2 points. So this is how we get the steepest descent direction. I will show the calculation of this gradient and everything while solving the problems. I am just saying the concept. So this is the method of steepest descent. We have one function value at x of t. Then we, to get the value of function at xt plus 1, we get we take in, we replace dt by minus of del of f of xt. Here x naught is like starting point, so we can take x for at time step t. We can take f of xt. So at every iteration we'll have the, we'll multiply by the descent, steepest descent direction at every iteration, and alpha is an arbitrary constant. The thing is that when we are converting this whole, writing this equation, we'll get the whole equation in terms of only one variable, that is alpha. We won't be getting, suppose here I have already told that x is a function, a multivariate function, that it is a function of x1, x2, x3, x4. So when we are writing this in this format, we'll get the whole equation in the format of, in one particular format, that is only as a function of one variable, that is alpha. And now we know that this whole function is a now function of only univariate function, and we have seen how to solve a optimization problem for a single variable function in the last class, that is by this golden ratio method or the Newton-Raphson method, bisection method, interval halving method. So we can use any of these, of any of those four methods to get to the optimal solution, using, if we have only, if the function is only a variable, is a function is only depends on the value of alpha, that is only one variable. So this is the method of steepest descent. It will be more clear when you will be solving one problem. And the next method is the Newton's method. We have seen Newton's method for univariate functions, that is for single value optimization. The Newton's method is written in this format, that is xi plus 1 equal to xi minus f dash xi by f double dash of xi. So one is, so this Newton's method is also written in a quasi-Newton. If we cannot directly calculate the derivative by simple arithmetic, we will using numerical techniques. That is, I told our central difference and finite difference methods. So we will be using finite difference method to calculate the derivatives. So if we calculate derivatives using finite difference or numerical optimize or numerical methods, then it is called the quasi-Newton method. And this now Newton's method can be extended to the multivariate optimization problem. And in multivariate optimization, we will write the Newton's method in this format. That is f of x k plus 1 is equal to f of x k minus of del square f of xk whole inverse, this is inverse, okay, into del of f of xk. This del square is coming from where? From f double dash. You have seen that f double dash is in the denominator. If we take to the numerator, so this is a matrix. Since we're talking about multivariate functions, so they will be like it will be f is a function of 3 or 4 variables or maybe n variables. So when we have n variables, so this del square will come as a matrix. And we have told in the first class that del square will be a Hessian matrix. I think if you remember, this is how the del square f of xt is written. That is, this is called the Hessian matrix. F double dash x in multivariate form is called the Hessian matrix. So when you're taking the Newton's method, so this Hessian, we have to take the inverse of the Hessian matrix. It is del square f of xt into whole inverse, and we have to multiply by the del of f of xk. So this del of f of xk is coming from the first term, the numerator. Numerator will be same. For multivariate, it will be del of xk is the gradient of the function, and it will be multiplied by the inverse of the Hessian matrix. So in this Newton's method, the direction is given by this formula, that is minus of del square f of xk whole inverse into del of f of xk. And if del square, this first term, this Hessian matrix is positive semi-definite or positive semi-definite, then the direction sk is called the steepest descent direction in case of a Newton's method. Okay, so these are the two main methods that we are using for solving multivariate problems. One is the steepest descent direction method, and second is the Newton's method. In Newton's method, the only advantage is that we won't be using any parameter alpha. We will be directly using the this second derivative, while whereas in steepest descent method, we will have a parameter alpha, and we have to calculate the function, that optimize the function with respect to alpha in by the methods of single value optimization. So these are the two main methods, and there are three theorems related to convex function. The first thing is that derivations are done in the class. I won't be doing the derivations here. If you want to see the derivations, you can just go to the lecture. I think lecture 11. I think, yeah. So the function fx is convex if for any 2 points x1 and x2, this condition is met. F of x2 is greater than equal to f of x1 plus del of f of t into x1 into x2 minus x1. Second theorem is a function f of x is convex if the Hessian matrix Hx is positive semi-definite. So this is again we have seen for that minima. This in the for a convex function we'll always have a minima, and for a minima in 1D, what is the condition? This f double dash x should be less than equal to 0. So if it is a multivariate problem, so in that case del square f of x is less than equal to 0. So this sorry, it is not less than, this is greater than equal to 0. So less than equal to 0 is for the maxima, for minima it is greater than equal to 0. So in if you're talking about multivariate functions, then this del square f of x should be greater than equal to 0. This is called a positive semi-definite or positive definite matrix. It is positive definite if it is strictly greater than. If it is strictly greater than 0, then it is called a positive definite. If it is greater than equal to 0, it is positive semi-definite. So to have a convex function, this positive semi-definite condition is sufficient. And how do we define if a matrix is positive semi-definite or positive definite? There are two ways. One is that we calculate the eigenvalues, and if all the eigenvalues are positive, then it is a positive definite matrix. And the second way of checking a matrix whether it is a positive definite or not is by calculating the determinant. If the principal determinant is greater than equal to 0, then the matrix is positive definite. And last theorem is that local minima of a convex function is also a global minima. Since in a convex function is only having, there is no, if function is like this, then it is not a convex function. For a convex function, there will be one minima, and the local minima will be the global minima. So this is the about the three theorems in convex function. And lastly, how we define problem in convex optimization problem. So convex optimization problem is defined as minima is a function of f of x. It is subject to the constraint gx less than equal to 0, where gx is the convex function, and hx is equal to 0, where hx is a linear function. And I think this derivation also is done in class, like why do we select hx equal to 0 and gx less than equal to 0. And if hx is not a linear function, hx equal to 0 is not a linear function, in that case it will be a non-convex problem. Okay, so this is, so we will be looking into the details of this constraint optimization problem in the next lecture. It is when we will be seeing these Lagrangian multiplier methods and all. So in this class we will be just looking into the initial methods, that is space descent and the Newton's method. Okay, I hope it is clear. These are the basic concepts regarding uh, this convex function and the methods to solve convex function. So we'll be looking into some problems now. Okay, the first problem is given as this: the optimal solution of the objective function.
Like little zoom it, sir.
Yeah, yeah. Can you see the? Is it legible now?
Yes, yes.
Okay. And okay, one second. Yeah. The optimal solution of objective function f of x is equal to x. Now f of x is given. F of x is given as what? X1 square minus of 2x1 x2 plus 4 x2 square. So this function is given. This is a function of two variables, that is x1 and x2. Is the optimal solution of this objective function is to be determined by using the Newton's method. If the initial point x naught is equal to minus 3 comma 1, which is also equals to minus 3 1 whole transpose. The optimal solution in the direction obtained at the initial point is x1 equal to alpha comma beta of our whole transpose. So we have obtained some optimal solution x1 is equal to alpha comma beta after doing the Newton's method. So we have to find the value of alpha and beta. Now we have seen the Newton's method. What is the Newton's method? It is x1 is equal to x naught minus del square f of x whole sorry, x1 transpose equal to x0 transpose del square f of x whole inverse into del of f of x. Okay, so we have to calculate the two gradients, that is del of f of x and del square f of x. So we'll be first doing this. So now what del of f of x is given as this matrix, this del f by del x and del f by del y. Okay, so this is the matrix. So we have to do the partial derivatives of partial derivative of f with respect to x and the partial derivative of f with respect to y. So let's calculate that. Uh, so del f by del x, what will be? It will be, oh sorry, it will be x instead of y. I'm sorry. This x1 and x2, not x and 1, sorry. So del f by del x1, so it will be 2x1 minus of 2x2, right? We have only these two, and del f by del x2 is equals to it will be minus 2x1 plus 8x2. Okay, we're just taking a partial derivative of this function with respect to x1 and x2. Now we are given that the initial point is minus 3 and 1, so we have to calculate the value of, see, this is at x naught. Okay, this is at x naught. So del, I am not, this is the formula I am writing it. So del of f of x naught we have to calculate, so we will be doing that. Equal to 2 into minus 3 minus of 2 into 1 is equal to minus 8, and del f by del x2 it will be minus 2 into minus 3 will be how much? 6 plus 8 equal to 40. So does del of f of x naught will be equal to how much? Minus 8 comma 14, right? So in case of this multivariate optimization, we will be writing everything in terms of matrix because we have more than one variables. Now you have to calculate this first term. This is del square f of x naught to the power whole inverse. So before getting inverse, we should get del square f of x. So this del square f of x is given by this matrix del square f by del x1, del square f by del x1, del x2. Okay, this is also called the Hessian matrix. So we have to calculate these terms, right? Del square by del x1 square, del square by del x2 square. So we have del f by del x1 and del f by del x2. From this, we will calculate the other terms. So del square f by del x1 square is equal to, if you take the derivative with respect to x1 again, so it will be 2. From here, we will have del square f by del x2 square is equal to 8, because del f by del x2 divided, again if we take derivative, this term will vanish, only this term will be remaining, so it will be 8. And del square f by del x1 del x2, you can take if we have del f by del x2, we just take the derivative with respect to x1 here, so it will give minus 2, and if we take from here also, it will be coming minus 2 only. So we have got the Hessian matrix. The values are how much? 2, minus 2, minus 2, and 8. So I will take the uh, inverse of this Hessian matrix. So I hope you remember the way of taking inverse. The inverse is calculated as, suppose if we have a matrix A, then A inverse is equal to adjunct of A by determinant of A. And how do we calculate the adjunct? It is the transpose of the cofactor matrix divided by determinant of n. And how do we calculate cofactor matrix? It will be minus 1 to the power I plus j into mij divided by adjunct of. So m minus 1 I plus j is the suppose it is the index of every term. For this here it will be I is 1, j is 1. For here I is 1, j is 2, like that. So an mij is the minor for this uh, for this first term. The mij will be 8. That is, if it is 3 by 3 matrix, then it will be 8. So how will say, suppose I will just show an example. Okay, So if we have to get the M11, so M11 will be, if you have to cut this row, you have to cut this column, that the remaining terms that is remain, we have to take a determinant of this thing. So it will be 60 minus of 63. So it is minus 3. It's like that. Similarly, if it is for 2, we have to cut this row, cut this column and cut this row, and take the remaining terms. And from that remaining matrix, whatever remains, we take the determinant. This is how we calculate Mij. Okay. I hope you have learned these things in undergraduate or even during 11th and 12th. So just I'm just refreshing it. It's not like okay. So for this matrix, we'll calculate the inverse. Till we have what? Now we have to take 1 by determinant A. Determinant A is what will determine? Determinant will be 2 into 8 minus of 16 minus of 4. 2 into 2, 4. 16 minus 4 is 12. So determinant A is coming here. So adjunct A. For now, for adjunct A, we have to take for all the terms. For the first term, the adjunct will be how much? Minus 1 to the power 1 plus 1, that is 1 into Mij will be remaining, cutting these rows, only 8 will be remaining. So 8 will be coming here. Now for the second term, that is for this term. So the power is minus 1 to the power of I plus n. So minus 1 to the power of 1 plus 2 is minus 1 to the power 3 is minus 1. So minus 1. So it will be minus 1 into, and what will be the minor? The minor will be, if you cut these two rows, it will be minus. Again here minus 1 into minus 2 same, and here it will be. So it will be 1 by 12 into this matrix 8, 2, 2. So this is we got this term. So now let us calculate the optimal solution. That is x1 transpose equal to, what was x naught? Initial value was minus 3 and 1, minus of del square x whole long, for that is 1 by 12. We have del square of x. It's 8, 2, 2, 2. We got this del square f whole inverse into del of f of x. Del of f of x is how much? Minus 8 comma 14. Okay. So it will be minus 3, 1, minus of 1 by 12. So we will do row multiplication. You know 8 into minus 8 plus 2 into 14. So how much will be? Minus 64 plus 28. Okay. Again 2 into minus 8 minus 16 plus 20. 3, 1 minus of 1 by 12 into minus 60 plus 20 is equal to minus 36, and 28 minus 16 is 12. So it is minus 3, 1 minus of minus 3, 1. So both the two matrices are same. So minus 3, 1 minus of minus 3, 1 is equal to 0. So this is the solution. So the x1 is 0 comma 0. So this alpha value will be 0 and beta will also be 0. So it will be the second option. Okay. I hope it is clear. All the steps, the methods in the steps, right? Okay. We'll proceed to the next one or similar next question. Okay, let us solve this using this steepest descent method. That is f of xy is, here again you have to find the minimum of the function. This is a convex function. We have to find the minimum of this function f is equal to x square plus y square. Take x not equal to 2 comma 1. Initial value is 2 comma. So in steepest descent, what we need? We need only that is del of f of x, right? Where did you see? Yeah. So we need alpha and del transpose of f of x into again of del of f of x. So we need only del of f of x, and alpha will be taking as arbitrary constant. So let us take del of f of x. It is equal to this matrix del f by del y. So what we will get, del f by del x is 2x and del f by del y is 2y. Okay. So let us see now x1 is equals to x naught minus alpha whole transpose into so yeah, this term is the del of f of x transpose. Okay, that if you write in a column form, the column form will be the transpose form, and the row form will be the normal form. This is x naught transpose. So this is x naught transpose. Okay, so x naught transpose is how much? 2 comma 1 minus of alpha. This it will be 2x comma 2y. Okay, so it will be 2 comma 1 of alpha 4x square, and it will be 4y square, right? So it's equal to 2 minus alpha into 4x square, 1 minus alpha into 4y square. So we got x1 transpose, that is x1 transpose is how much? X y transpose. So we have got these two values for x1. What will be the after first is x1 will be 2 minus alpha into 4x. I think I have done something. One second, okay. I think I have missed something. Okay, okay. Sorry, sorry. Yeah, this is fine. So this is x and y at the initial position. Okay, just remember that this whole thing is at the initial point is how much? 2 comma 1. So we'll be substituting 2 and 1 here, which is equals to 2 minus alpha into 4 into 4 will be 16, 1 minus alpha into 4 into 1 will be 4, right? Because y x naught equals to 2 and y naught equals to 1. This is given. So we have this for function x1 and y1 only in terms of alpha. We have to substitute this in this function, that is f of x1. So now it will be coming f of alpha is equal to 2 minus 16 alpha whole square plus 1 minus 4 alpha whole square. So the thing is that this is the derivative, like we can directly take the derivative and get the value, or we can also use the Newton's method or the this one golden section search method. So we'll you know these methods. I will be directly taking derivative and finding the solution in terms of alpha only. So we'll take f dash of alpha equal to 2 into 2 minus 16 alpha into minus 16 plus 2 into 1 minus 4 alpha into minus 4. So f dash alpha should be equal to 0 for getting a minimum. So it will be, I think, 2 and 2 will go out here. So minus and minus we can get cancelled since it's 0 this side. So you can take 4 and it will be 4. 8 minus 64 alpha plus 1 minus 4 alpha. Alpha is equal to 9 by 68. Okay, if we substitute alpha is equal to 9 by 68 in this solution, so now x1 comma y1 is equals to how much? 2 by 2 minus 16 into 9 by 68, it is 1 minus 4 into 9 by 68. Did I do some mistake here? Okay. Sorry, my bad. In the steepest descent formula, we need not multiply with del of f of x. We have directly multiply with the descent direction. So this formula it is into dt, but the thing is that this is for f of x. But when we calculate x, it will be x t plus 1 equal to x t minus of alpha into del of f. So we will take only the derivative. We did not take the multiplication of derivative. Sorry, this is my mistake. So this term will be vanishing from here. So I think it will be what? 2 minus alpha into 2x, 1 minus alpha into 2y. This is equal to x naught equal to x naught and y naught. So these values will come as equal to x naught equal to, so 2 minus 4 alpha, 1 minus 2 alpha. So we'll get a different equation. So if you take the derivative, 2 minus 4 alpha into minus 4 plus 2 into 1 minus 2 alpha into minus 2. So this is equal to 0. So 2 and 2 will go out, minus and minus will go out. So 2 into this 2 will remain. 4 minus 8 alpha plus 1 minus 2 alpha. This is equal to alpha is equals to 1 by 2. And now if you substitute, you have to substitute the value of alpha in this value of x1 and y1. x1 y1 is equals to 2 minus 4 by 2, 1 minus 2 by equal to 0 comma 0. Okay, this is clear. I am sorry, like it's for CPS decision, I had some misinterpretation. I hope this is clear.
We are taking the direct derivative, sir. Can you please explain once again?
Yeah,
Direct
yeah,
derivative here.
directly this the next value of the function at the next iteration, the x1 will be coming as x naught t. That is a whatever value, like what is the uh, not value, the points at the x naught minus of
Yes.
alpha into del of f of x.
Okay. Okay.
Okay, this condition was this for one thing. Okay, I'll just, yeah. So you have to multiply dt when you're taking the function to get to the this steepest descent function. We are doing this at the f
Okay.
of x, that is function value. The function of f of x t plus 1 equal to f of x t plus of alpha into del of f of x t into dt. So from there it comes the how we get the value of dt. It comes from this condition.
Okay.
Okay,
Okay.
it comes from then. But when I calculating the this is what will be the points, that is at what point we'll get the minimum. For that we will take only one derivative, and then
Okay.
x t plus 1 equal x t minus alpha into del of it. That's all.
Okay. Okay.
Okay, yeah. Okay, so next question is like the value of a and b. So that f of x of y equal to x square plus ax plus what this function is given has a local minimum value of 17 at 1 comma 0. Now for getting a local minimum, what are the conditions? First condition is that del of f of x comma y is equal to 0. That is, first derivative is 0, and the del square f of x comma y is greater than equals to 0 if we want the minimum. So we'll get to find the value of a and b. So we'll go to this first condition. So for this del of f of x y, it will be del f by del x and del f by del. So let's calculate del f by del x. What will be del f by del x? It will be 2x plus a, right? 2x plus a, and del f by del y will be equal to 2y. And if we solve this, we will get this is equal to 0 at the initial point, and at the sorry at the minimum value. The minimum value is given at what point? At 1 comma 0. So it will be 2 plus a by 0. So a is equal to minus 2. Now we got a is equal to minus 2, and what else is given? That has a minimum value of 17 at 1 comma 0. You put 17 here, and then you can find the value of beta. So f of x y is equal to 17. X is 2 square plus this is minus 2 into, oh, sorry, x is 1, sorry, not 2. X is 1, 2 in minus 2 into 1, y is 0, so it will be 0 plus b. So we do minus 1 plus b, b is equals to 18. So the value of a and b are minus 2 and 18. This is the option. You can also check this the second derivative also. The second derivative will be if we take, so it again del square f by del x square will be how much? It will be 2. Del square f by del x del y, this is 0. Del square f by del again this is 0, and del square f by del y square is equal to 2. Which is equal to 4. It is greater than 0. So we will have a minima only in this for this function. Yeah, this was pretty easy. You will just check this first derivative condition, and based on that only you'll have to get the solution. Okay, we'll see the next question. Consider a function g f of x y equal to minus x to the power 4 y to the power 4. Which of the following is the correct statement about the function? So now thing is that we have to see the function as global minima but not global maxima. So thing is, we have to check if this function is a concave function or a convex function. Now how do we check if a function is a concave or convex? So we'll use this criterion. A function f of x is convex if the Hessian matrix is a positive semi-definite. We'll get find the Hessian matrix and then we will see if the Hessian matrix value is positive or negative. So it is positive definite or semi or negative definite. Okay. So we have g of xy. So first let us for how are terms from Hessian matrix. So we'll first get the terms first. Del x by del square g by. Okay, let's calculate the term one by one. Del g by del x is equal to, so 4 of x cube y to the power 4. Del g by del y is equals to minus of 4x to the power 4 y cube. Okay. Now del square g by del x square. So it will be minus 12 into x square y to the power 4. Del square g by del y square equal to minus 12 into x to the power 4 y square, and del square g by del x del y is equal to, I think, minus 16 into x cube y cube. We'll get the same from this. So the Hessian matrix will be what? It will be minus 12 x square y to the power 4 minus 16 x cube y cube minus 16 x cube y cube minus 12 x to the power 4 y square. So to see this, it is a positive definite. So one other way of checking is that we have to see if the principal determinant is positive or it is positive or negative. So we'll take the determinant of this function, which will be 144 into x to the power 6 y to the power 6 minus of 256 into x to the power 6 y to the power 6. So it will be, I think, minus of 112 x to the power 6 y to the power 6. Now this term will always be positive because the even power. So the Hessian matrix will always be negative. Now if the Hessian matrix is negative, we say that it is a concave function, and for a concave function we always have a global maxima. So the function will have a global maxima but no global minima. Okay, the second option. This is how you check if a function will have a, you have to it's a maximization problem or a minimization problem. You just check the Hessian matrix and see if it is positive definite or negative definite. Okay, I hope this is clear. This is a basic problem again. Okay, next second problem. This is again a univariate problem only. It is not a multivariate problem. It's just this is the calculation, so I'll just do the calculations. The concentration of a particular drug in a blood in time t after taking the dose at x units where xt is equal to 0.3 t e to the minus 1.1 t for the first 3 hours. Which of the following gives the correct maximum concentration and the time it occurs up to 4 decimal places? So to get the time, we have to do the maximization of this problem. To get the maximum, again we have to do x dash of this, that is derivative of this function should be equal to 0 and double derivative should be less than 0. So our x of t is given as 0.3 t, okay, and it was 3 less than equal to 3 hours. So we have to do the maximum. So let us take x dash of t is equal to 0.3. Now we will have to use the chain rule because it is a function multiplication of two. It is a non-linear function, that's why. So it will be, if you take it with respect to first, it will be minus e to the minus 1.1 t plus minus 1.1 into t This is with respect derivative with respect to t. And so this is how you do the part. This one multiplication like this one derivative by parts. Sorry. So it will be 0.3 and e to the power minus of 1.1 t. It will be 1 minus of 1.1. Now this derivative should be equal to 0 to get to any maxima or to get to optimal solution. So this value can never be 0. This exponential term can never be 0. So this will be equal to t is equal to 1 by 1.1. This is equal to 0.9091. So at this time, hours. At this time, we'll have the maximum concentration. And what will be the maximum concentration? We'll have to just substitute this value in the function. 0.3 into 0.9091. So if we substitute and all, then it is just a calculation term. So we'll get this 0.1003 in the option A. Sorry, it will be option C. You can do the calculation and see. This is a simple calculation. I won't be doing the calculation. Okay. Recall that this is again a conceptual problem. Recall that Newton's method can be used to find an approximate solution of a function f of x equal to 0. We have already seen that for if we want to get a root of a solution, we have to take that xn plus 1 equal to xn minus of f of xn by f dash of xn. While modeling an epidemic to compute how many individuals are still susceptible at the end of the epidemic, one needs to solve the equation s minus 10 of ln s plus 6 equal to 0 for s. Here, s is the number of susceptible measured in thousands. If we consider s equal to x, then we can use Newton's method to approximate the roots of the equation x minus 10 ln x plus 6 equal to 0. While setting up Newton's method for this problem, answer the following. The value of x n plus 1. So we have, if we know xn, we can get to the next, that is the value of xn plus 1, that is in the next step. So let us see the function equal to x minus 10 plus 6. Now Newton's method is x n plus 1 is equal to x n minus of f of x n by f dash of x n. So we need to find f dash of x n. F dash of x n will come as what? So dx by dx is 1 minus 10 by x n. So this will be 0 equal to 1 minus of 10 by x and difference of log of x equal to 1 by x. So let's substitute in this fellow in this formula xn plus 1 is equal to xn minus f of xn is how much? Xn minus 10 ln xn plus 6 1 minus 10 by okay, we'll do the xn minus of xn into equal to xn minus, so we'll have xn minus 10 at denominator. We take xn common from here, so xn minus 10 plus xn. Sorry, it is not plus, it is.
So xn minus 10 by xn as a denominator.
Oh no, I have taken this
Okay.
xn to the numerator here.
Okay.
And
Okay.
now here I am taking this xn and xn common, like out of this term and taken as a common term. Okay. So and now taking the whole denominator. So xn minus 10 will come here. So it is minus xn plus 10 ln xn minus 6. I think xn will get cancelled. So it will be xn into, let's see what is the, yeah, I think this is the answer, no? 10 into xn into ln xn, 10 into xn ln xn minus 16 of xn by xn minus 10, I think. Yeah, option C. Okay, this is just simple arithmetic only. After, if you know the method, that's always the proceed with the arithmetic. So if we proceed with x1 equal to 1 as the initial approximation and next guess x2. So in case of n, here will be n is equal to 1. So x2 will be how much? Uh, sorry, xn is equal to, what is, yeah, that is x1 is equal to 1. So in place of xn, we will put 1. 10 into log of 1 is 0 minus 16 divided by 1 minus 10 is equal to minus 16 by minus 16 by 9. So it will be 16 by 9, the first option. It's just substituting the values in the formula, that's all. Okay. Let's proceed to the next question. Minimize f of x1 x2 is equal to x1 minus x2 plus 2x1 square minus 2x1 x2 plus x2 square using Newton's method. Consider a starting point as x1 equal to 0, 0. Okay, we have seen Newton's method. Again, we have to do the procedure in the same way. So yeah, let us see. So first we have to calculate del of f of x. So it will be what? Del f by del x1, del f by del x2. So del f by del x1 is how much? It will be 1 plus 4x1 plus 2x2, right? So if I do any mistakes, just point out. Okay, I am also doing the calculation for the first time here. So for del f by del x2 minus 1 plus 2x1 plus 2x2, right? Okay. So we have del f by del x1. We need the value at 0, 0. Actually, these two terms will be 0, so it will be 1, minus 1. Okay. Now we will have to calculate the Hessian matrix. It is del square f of x. So the first term will be del square f by f of x1. So del square f by del x1 square. So we will be taking the derivative of. So we'll get the values of this one. So del square f by del x1 square is equals to 10 into, we taken derivative of the first row. This is del f by del x1. Take the derivative of this to get del square f by del x1 square. 1 plus 4x1 plus equal to 4. square is del by del x2 into minus 1 plus 2x1 plus 2x, which is equal to 2. And thirdly, del square f by del x1 del x2. So you can just calculate, take derivative with respect to del of x2 of this term. So it will be coming, I think, 2 only. So the Hessian matrix will be 4, 2, 2, 2. Now I have to take the inverse of this. Is equal to 1 by determinant of this del square f into adjunct of del square f. So determinant is how much? 4 to the 8 minus 4 is equal to 4. For the first term, it will be 2. I have seen that is, if you cancel this row and column, this term will be remaining, so it will be coming here. For 2, it will be 4, and for this 2, it will be minus 2. Since minus 1 to the power I plus again 1 plus 2 is minus 1, so minus 1 into this one, and this again minus 2. So this is a del square f we got. So let us now calculate the term using Newton's method. X1 is given as 0, 0, sorry, minus of 1 by 4, 2 minus 2 minus 2, 4, and del square f is 1, del of f is 1, minus 1. Okay, so it is equal to minus 1 by 4. 2 into 1 plus minus 2 into minus 1 is minus 2 plus 2, it will be 4, minus 2 minus 4, I think it is minus 2 minus 4 is equal to minus 6. So it will be what? Minus 1, 3 by 2. Solution is minus 1, 3 by 2. Now the function f of x, 2, this function is a long function, I think. Yeah, we will do the calculation for that. Is a convex function or a concave function? Again, we have to calculate Hessian matrix for that. Wait a minute, then I will just. Okay. Okay, let me just copy the function here. Question number 9. X1 square minus x2 square minus x3 square. Okay, so this is the function of 3 variables. So x1 square so for 3 variables we will see minus x3 square plus 2x1 x3 plus 2x1 x2 2x1 x2 plus 2 plus 4x1 minus 5x3 plus 2. So this is a function of a 3 variables. So the Hessian matrix will be a 3 by 3 matrix. So again we'll have to do find the values. So let's find the del f by del x1 is equal to 2x1 plus 2x3 plus 2x2 minus 4. Del f by del x2 is equals to minus 2x2 plus 2x1, and del f by del x3 is equals to minus 2x3 plus 2x1 minus 5. Okay, so the terms of the Hessian matrix, again we have to take derivative of all the terms. Del squared f by del x1 squared, derivative with respect to x1, so it will be 2 del squared f by del x1 del x2, it will be, I think, minus 2, or no, sorry, del x2 will be equal to 2 only, and del squared f by del x1 del x3, take derivative of this with respect to x3, so it will be 2 again. Now next, del square f by del x2 square, so it will be coming from here, it will be minus 2 del square f by del x2 x3, it will be 0 because x1 x2 will be same as 2 only. And lastly, del square f by del x3 square, it will be minus 2, and other terms are fixed. So we'll get the Hessian matrix. It will be 2, 2, 2. So del square by del x1 x2 equal 2, del square by del x2 square minus 2. So this is the Hessian matrix. Okay, you have seen the formula, right? So this is how it comes. I'll just del square f by del x1 square, del square f by del x2 square, and del square f by del x3, del square f x2, del square f by del x1 x3, again del square f by del x2 x3. The Hessian matrix. So to see if it is a positive definition, so we have to take the determinant of h. So it will be 2 into 4 plus 2 into 2 4. So this is greater than 0. So this is determinant greater than 0. Again, so this is determinant greater than 0. So it is a positive definite matrix. So it will be a it's false. Why is it false? 2 4 plus 2 into 0 minus of. Okay, sorry. For positive definite, you have to see all the determinants, right? This is the 3 by 3 determinant. Now we have to see the determinant. Second is h 2 by 2. The 2 by 2 determinants we have to see the principal. So it will be determinant of this function. So this is equals to 4. This is also greater than 0. But when you're getting to h1 comma 1, so it will be minus 2. Since this value is minus 2, this is less than 0. So the h is not positive definite. So the function is not a convex function. Okay, I hope you understood this. So the thing is that when you're checking for positive definite, you have to see all the three determinants. So one is this 1 by 1 determinant, 2 by 2 determinant, and 3 by 3 determinant. So all the three determinants you have to see, and if all the three are greater than 0, then only it will be a positive definite matrix. Okay, just be clear. Just checking only one determinant is not enough. I hope this is clear. So okay, let's proceed to the last problem for today. The minimum of the function f of x, this is the what x square plus y square plus 2x minus plus 4, is to be determined by using an optimization method, using x not equal to 2 comma 1 transpose as the initial estimate of optimization, optimal value of the variable, and the optimal function value are. So yeah, we'll do by steepest descent again. We want to go steepest descent since no method is mentioned specifically. Del of f of x equal to del f by del x, del f by del y. So initial point is 2 comma 1. So comma so x 1 is equal to 2 comma 1 minus of alpha into del of f of x, 6 equal to 2 minus 6 alpha, 1 minus 2 alpha. So x1 will be a function of these two variable, that is x1 comma y1. We'll substitute x1 and y1 in the function. Equal to 2 minus 6 alpha whole square plus so we'll take f dash x, f dash alpha will take 2 into 2 minus 6 alpha into minus 6 plus 2 into 1 minus 2 alpha. Twelve. 2 into 2 differential derivative is 0 for this, the last term. So this is equal to 0. Minus 12 into 2 minus 6 alpha plus 12 minus 24 minus 24 minus 12 36 36 plus the minus alpha is equals to 1 by 2. So we'll substitute alpha equal to 1 by 2 here. So we'll get x1 and y1. 2 minus 3, 1 minus 1, I think. Will be minus 1 comma 0. So the function value will be minimum at minus 1 comma 0, and the value of the function is equal to minus 1 whole square plus 0 is 2 into minus 1 plus 4. 5 minus 2 is equal to 3. So it will be minus 1 comma 0 and 3. Okay, this is again by steepest descent method only. Now for an optimization problem, a local minima is unique, it is a global minima. It is true. Yeah, if you have any doubts in any of the problems solved today, you can ask me now. I am done with the
What is the
blackboard.
wow? Can you
Yeah,
explain the
yeah. What?
last one?
This
Problem 11.
11 is that if for an optimization problem, if the local minima is unique, so the thing is that if
Only
this is
one.
a kind of function, there are how many? Four local minimas, right? So this is not a unique local minima. So among these four local minima, this is the global minima. So there will be one global minima among four local minimas. But here it says the local minima is unique. So means that only one local minima is there.
Okay, okay,
So that
okay,
local minima will be a global minima. That's
okay.
all. Anything else you have to ask? X is real. Like, can you elaborate? Like, I don't understand. What do you mean by X is real?
How to check whether the function is concave? How to check, sir? If it is, how to check it is a concave? How to apply the theorem?
Yeah. Concave is like again this thing. Now we'll see the Hessian matrix only.
Okay,
Here we found that this thing is less than this is not convex because one is less than 0. For
okay,
concave, all the Hessian principal determinants, all the determinants should be less than 0. It is
okay,
not like only 2 greater than 0 and 1 less than 0. It's not like that. All should be less than 0. Like of the Hessian matrix, all the principal determinants must be less than 0, or all the
okay,
eigenvalues must be less than 0.
okay,
If either of these conditions satisfies, then it is a positive, it is a sorry negative definite matrix, and in that case, there will be a concave function.
okay, okay.
X values are, yeah, you are asking if in a problem they are taking X as a real values. Real values means it can take any value from minus infinity to plus infinity. So a real number line consists of the rational numbers, irrational numbers, integers, and also yeah everything. It shouldn't be a complex value. That is that you know complex numbers, right? 1 plus 2i or 2 plus 3i, like that. That imaginary part shouldn't be there. So if it is not there, it is simple real values. That is what X is a real values mean. We are always mostly dealing with real values only. Complex when we are doing it complex analysis, then it will be slight. All the calculation methods will be different for complex numbers. Like you can say the square root of minus 2. This is a complex number. You cannot find the square root of a negative number. So it is called root 2 of imaginary. Root 2 of into imaginary iota. Okay. So it is like this is a complex number. It's like that. So if these complications are not there, then it is a real number. All values that are between minus infinity, plus infinity, rational numbers, irrational numbers, integers, whole numbers, everything. Okay. Any other doubts? Sai Krishna, it's clear, right? That I have told our real numbers. I think it's basic thing only. Okay. Okay, then yeah, if there are no doubts, I will end the session. Yeah, and regarding the assignment solutions, you can just mail the professor or you can mail NPTEL directly. Yeah, you can mention the course number, the course ID, that is the NOC, I think this is the course. Yeah, course ID, the course ID is given, so you can mention the course ID and everything to NPTEL, and you can CC the supervisor, that is I think Rajiv Kumar Bhattacharya. Okay, you can CC the faculty and then write a mail to NPTEL. They will respond. Okay, if they don't respond, then just let me know in the next week. I will contact them. Okay. Okay then. Have a good evening. I will end this session. If there are any doubts, you can ask in the next class also. Okay. Bye bye.